Hey, all you cool cats and kittens. It's Mr. Lucan back with another video. We're going to start at chapter 7, which is all about exponential and logarithmic functions. Today, we're going to start off with section 7.1, which is exponential growth versus exponential decay. So, we're going to kind of talk about what those words mean. And it's just another way of another model that can be used for mathematics. So our EQ is how can I model exponential growth and decay using a graph or function? As a quick warm-up, we're going to evaluate each expression using the given value. So here, we haven't defined it yet, but this is what an exponential expression will look like. It has the variable in the exponent. So this is saying take 5 and multiply by 3 to the power of 2. Now we know from PEMDAS, or order of operations, that 3 to the second power, or exponents, has to occur first. 3 to the second is 9. 5 times 9 is 45. So that's the value for that first expression. Here we have 4 times 2.5. And 2.5 is going to be raised to the power of negative 2. Okay. Now for that, I can go to the calculator and type in 4 times 2.5 to the negative second power. I get 0.64. We're going to talk a little bit more about why it's a decimal and not a negative number in just a little bit. Here I have negative 1.5, and I'm going to multiply that by 0.5, which is the same as 1/2 to the fourth power. So again, if you have a calculator, awesome. If not, you can always use the Schoology link that's posted to do all the same stuff. And I'm going to show you a couple of tricks on the calculator as well to the fourth power. And I get negative 0.09375. Okay. So we're going to be dealing a lot with exponents, which is why where the word exponential comes from. So just keep that in mind. All right. So the definition of an exponential function is any function where the independent variable, and we think in math of the independent variable is being tied to the letter x, as anytime the independent variable is the exponent of the function. Okay. So the general exponential function is going to be written like this: y equals a times b to the x, where a we're going to call the start value, and b is what's going to be called the growth factor. We're also going to call it from time to time, it'll be called the decay factor, and we'll talk about when it is each type. So sometimes it's a growth factor, sometimes it's a decay factor. Some people just call it growth factor all the time. So that's kind of how this is set up. And then x is the input or the independent variable. Okay. So let's look at what an exponential function looks like with numbers in it, and then take a look at what happens when we graph it. A lot of times in math, right, if you want to get an idea of what a graph looks like, you go from a couple negative numbers, a couple positive numbers. So I'm going to do from -2 to 2 for x values and see what kind of y values I get. Now, I could type each one of these individually, just like I did in the warm-up. But what I'm going to do instead, if I know I have lots of values to type in, I'm going to go to y equals, and I'm going to just type the equation in exactly as it looks. So 1.5 times 2 to the power of x. This is the variable button on your calculator right next to the alpha key. Now I'm going to go to the table function. So table is second graph. And now I can see it has all of the positive x values over here on the left side. I'm going to go back just a little bit to -2. I'm going to use those numbers to fill in my table. So 0.375, 0.75, 1.5, 3, and 6. Okay. Now, I don't want to get into this too much immediately, but here's where these numbers show up in this table. Okay. That 1.5, that's our start value. which is the y value when x is 0. Okay, so that's going to show up there. So it's again not like a coincidence. These numbers actually do show up in the table. And you might ask yourself, well, where does 2 show up? Because I see the number 2 in the equation, but there's no 2 besides that in the table. But the 2 shows up as the pattern for how do you get from one number to the next number. So exponential functions have a pattern of multiplication in the y values. So to get the next y value, all you're going to do is take the previous y value and multiply by 2. Okay? But let's take a look at a graph of this real quick. Negative 2 comma 0.375. Now, this is not going to be exact. You're just going to do your best. The next one was negative 1 comma 0.75. And then 0 was 1.5. And then 2, or for positive 1, it was 3. 1, 2, 3. And then for positive 2, the y value is 6, 4, 5, 6. Okay, so we get this kind of set of points, and the question is, what do we do with this? Okay, we just spent a good chunk of time in second trimester talking about parabolas, which look like that. Okay, what happens here with these points? What does this graph look like? And so we can see that the points are increasing up and up and up. If I take a look at the graph on here, what's interesting is, and you can't see this super well, but I'll show you on Desmos in a little bit, that this blue line is getting closer and closer to 0, but it actually doesn't cross 0. So if we were to use technology and zoomed in a little bit, which again I'll do in a little while, what happens is this gets closer and closer to 0, but never actually goes negative. And we can see that too in the table. If you just keep going up and up and up, see how these numbers get really small, 0.0015. This is scientific notation, meaning there's even more zeros before the number, but it never actually gets to 0. And we'll discuss that more in a little bit. Okay, so let's try another one where it's just y equals, so there's no start value given to us here. Okay, so I'm going to get rid of that. And then since there's no start value, I can just put 0.5 to the power of x. So now if I go to the table, I don't care about negative 13. I want negative 2 to 2. So negative 2 is 4. Just in a different color. 4, and then 2, and then 1, 0.5, and 0.25. So what's kind of interesting here, the 0.5 is what you have to multiply, just like in the previous problem. I'm going to multiply by 0.5 to get to the next number. Half of 4 is 2, half of 2 is 1, half of 1 is 0.5, and so on. But then our start value here was actually 1. So what we could have done is we could have written this equation like this. Remember, most of the time in math, if there's a number missing in front of another number or a variable, most of the time it's going to be a 1. In this case, that missing 1 that wasn't written shows up as our start value in the table. So if I graph these points now, negative 2 comma 4, negative 1, 2, 3, 4, negative 1 comma 2, 0 comma 1, 1 comma 0.5, and 2 comma 0.25. I get kind of the same look, but on the other side of the graph, right? It's flipped horizontally. And sure enough, if I go to the graph, I see that it has that same look. It comes down. But if I go to the table, 0.5, right, these numbers are getting smaller and smaller, but they're not actually going to 0. So I have something like this, and I get close, but never actually touches 0, and it'll continue going on to the right. Okay, so we're going to talk about the difference between these two graphs. They're both exponential, but we're going to kind of put some more definition on the difference between these. Okay, so here's a computer-generated model using Desmos of the graphs we just did. Okay, this first graph, since it starts towards 0 and increases, this is what we call exponential growth. Okay, and what we're going to see is your graph will show exponential growth anytime the growth factor is bigger than 1. Okay, so if the growth factor is bigger than 1, you're gonna see the graph start low and then shoot upwards as you move from left to right. Okay, and then not super important, but the y-intercept of the graph is the start value, which again we are using the letter A. Y equals, well, it's always going to be the coordinate 0, comma A. 0, comma A. Okay. So we have exponential growth if the growth factor is bigger than 1. And then here, if our growth factor is actually 0.5, which is what leads us to this exponential decay look. I'm going to show you that in just a second on Desmos as well. But this is actually going to happen anytime that the b value is less than 1. But by definition, the b value has to be bigger than 0. Having a negative growth factor is going to lead to a graph that doesn't really even, you can't even really put on a graph. So what we're going to say for this is b is less than 1, but greater than 0. So in mathematical terminology, it looks like this. So b is somewhere between 0 and 1 is when you get exponential decay. All right. Now, the other thing that we do have to talk about is this idea of this line that the graph gets really, really close to, but never quite touches. Right. Both of these are getting extremely close to that line, getting really, really close to 0, but never quite touching 0. So for both of these, doesn't, and this is super important, please, when you're sketching these, doesn't cross the x-axis. Okay, and that's what's called a horizontal asymptote. Okay, horizontal meaning it's just going side to side. The word asymptote is a line that a function approaches but never touches. So this is the real big vocab piece for today. An asymptote is a line that the graph gets really close to, but it never actually gets to that value. Okay. Every exponential, whether it's growth or decay, every single graph will have an asymptote. And in this case, every single graph will have a horizontal asymptote. Okay. So what I want to do real quick before we draw a picture and kind of wrap this thing up is I do want to show you a where did it go? Here we go. I want to show you Desmos real quick because there's some really interesting things that you can see on here. Here I have an A value of 1.5 and a B value of 2. So this is the first picture that we sketched, right? It starts at 1.5 and then it doubles from there. So it goes to 3, then goes to 6, and so on and so forth. Okay. If I change the A value, notice that me changing the start value is still growth, but when the start value is 4.1, now that's where the graph starts, it's 4.1. Okay. If I go negative, this is what's kind of interesting. If I go negative, meaning that I'm starting at a negative 2.3, which I can see on the graph, okay, but B is still positive 2, I know this is weird, but we still call this growth, okay? So this is what we call negative growth because it's going away from 0, right? It's starting at 0 and then boom, flies downwards. So it's still growth, but we consider it negative growth. If I bring this back to the positive 2 and I change the growth factor, okay, if I push the growth factor out to 3, you'll see that it makes the graph steeper. But the start value hasn't changed, right? I'm still starting at 2. It's just now I'm tripling every time. So I'm multiplying by 3. If I bring the closer the B value is to 1, okay? So if you get a growth factor of 1.07, you might say to yourself, my gosh, that's not even the same look. It's just like almost a flat line. But if you zoom out, you'll see eventually we do get the exact same look. Okay, so it's still exponential growth. It just looks a little different in this smaller window because the numbers aren't big enough yet to see that growth. But then if I go to 1, if I have a growth factor of 1, it's completely flat because multiplying by 1 doesn't actually change the number. So you'll never see a growth factor that's 1 because it's not growing and it's not decaying. Okay. But then what we see here is if I go to a number between 0 and 1, like 0.56, I get that decay look to it. So we have 4 types. There's positive growth, there's negative growth, there's negative decay, which is approaching 0 as you go left to right, and then there's positive decay. So 4 different types of graphs. We're going to summarize that real quick, but it's all about the A and B value. Okay, so the first type and the most common type that you're going to see is exponential growth. So starts close to 0 and increases. This occurs if A is positive and B is greater than 1. Okay, that's exponential, that's positive growth. The next one we looked at was positive decay. Positive decay. That looked like I start high, but I'm approaching 0. Don't like that. Okay. This occurs when the start value is still positive, but B is between 0 and 1. Okay, that growth factor is between 0 and 1. Get the mouse out of there, sorry. Then next we saw there's such thing as negative growth. Whoops. Don't need to write the word negative after I put the negative sign. So negative growth starts close to 0, but on the negative side, and then fires straight down, or not straight down, but is going away from 0. And this occurs when the start value is less than 0, but the growth factor is still bigger than 1. And our fourth and final graph that we have is negative decay. So this is where on the negative side we have a decay graph, meaning it's getting closer to 0. This occurs when we have a negative start value, but B is between 0 and 1. Okay, so those are the 4 different types of graphs that we have. What I'd like you to do now is pause the video real quick and just see if you can identify whether or not we have positive growth, negative growth, positive decay, or negative decay for each of these functions. So pause it real quick, see what you think, and then we'll wrap this up. All right, first one, this is positive 1.84 is greater, so that's growth. Okay, that's as simple as it is. The A value tells you positive or negative, B value tells you growth or decay. 8,000 is definitely positive, 3.26, that's definitely bigger than 1. 0.1 is a small number, but it's still positive. 5.09 is a growth factor. 7.3, that's positive. 0.64, here's our first decay. I should have mixed in some negatives, but I didn't. This is positive 0.95. That's close to 1, but it is still less, so that's decay. And then 1,212,000, definitely positive, but 0.004 is not growth. That's much smaller than 1, so that's going to be decay. And honestly, the reason we don't see much negative growth and decay is because it's tough in a real-world situation to have negative growth. And most of the time, you're going to see positive either growth or decay. So how can I model exponential growth and decay? A times b to the x. This is my start value. This is my growth factor. The one thing about the growth factor is it must be greater than 0. You cannot have a negative growth factor. Okay, that'll wrap it up. And yeah, now we're done.